All right, so let's go ahead and get started with the second part here. So once you guys have a chance to get into your Desmos activity and take a look at this, the main part of the Desmos activity really is filling in the rest of our unit circle in 15-degree increments. Now, we mentioned, zoom that out a little bit, if we know one of our values, we should be able to think about flipping and then using our symmetry and our quadrants to figure out the other four. What this allows us to do is to know kind of a completely filled in for 15-degree increment unit circle. So I will put either this one or something kind of similar. This one maybe has a little bit more radius filled in than I would like to see, but it allows you to now fill everything in terms of our X and Y coordinates. Let's address one more issue that you actually are not going to see in this Desmos activity. This Desmos activity deals with sine and cosine for this part. As you go through, you'll talk about the patterns, a little bit more about cosine, and then more sine and cosine. Now, this card sort is actually a more practice of fractions than practice of your trig. For example, if you think about cosine of 7 pi over 12, what you're looking to match it with, obviously it's not going to match with like 13 pi over 12, but what we're looking to match it with is one of the ones that's a sum or a difference. Now, it's much easier to start in the reverse. If you have a sum or a difference, you could go ahead and find a common denominator, combine, and simplify. That's going to tell you which one of these, if any, that it matches up with. You do have a miscellaneous file, some that aren't going to match up, but we should be able to, if we look for one we can do. So let's focus on that 7 pi over 12. Turns out, if we look at all these other ones, let's see. I don't see anything that jumps out of me. Like I don't see any 12s. But if I think about these common denominators, these ones would have a common denominator of 12, common denominator of 24, which maybe I could reduce to 12. But again, nothing kind of obvious there. So for all of these, start thinking about sorting them into two piles first. All the ones that have sums or differences. And this is just going to help you think about how to break apart those and recognize when you could split something up in a sum or when you could combine into a single trig function. So if I look at these, I'm going to have these three guys and then all the rest. So in this particular card sort, is it possible that you could have more than one card match up on our other group? Sure, right? You could have something where there's a sum and a difference, or two different sums, two different differences. So that's definitely a possibility. And then keep in mind your miscellaneous pile. So once you get done with that part, understanding how to apply the formula and fill in the rest of the unit circle is the big deal. The last slide that's an active slide on Desmos is slide 9, where it's actually kind of a fun slide where you're going to be able to turn on some graphs, play with some sliders, and you're going to like look at some Desmos math art essentially, and look at a cool design just by manipulating what's here, and then you can add a little bit if you want to introduce some new sliders or to play around with the shading some. Kind of some cool stuff there. In other words, if I get rid of some of this, some of the stuff, you can see how your parameters and your inequalities are going to create some cool graphs. So play around with that a little bit. And then slide 10 is just to leave some feedback and some comments. Y'all, I don't know if you can hear upstairs. It sounds like it's a herd of elephants. My husband and youngest are up there, and whenever you walk upstairs, you hear it in the basement. So I'm sorry if that isn't really loud coming through. It sounds like thunder and elephants here. I'm sure you guys have not quiet houses as well. So let's go ahead and take a look at what we want to do from here. Once we get comfortable with recognizing when we can do a sum and difference and how to kind of put those together and combine, we want to make sure we see how to apply this information to trig equations and trig inequalities, the two other things we've studied in this unit. Now, in terms of trig identities, We're not going to do a whole lot with integrating the sum and difference formulas into our trig identities. The one example you have in your WebAssign is looking at the co-function identities. In other words, taking sine and transforming into cosine, or cosine into sine, and how to use a sum and difference. If we have time, I'll walk you through the WebAssign on that, but just kind of minimal there. In terms of where you could use this, you have one example or one problem in your WebAssign is a trig equation. So I'm going to go ahead and stop this share, and we're going to look at a trig equation together. We'll write it out and take a look at how to use these parts to solve. So we'll continue to focus on sine and cosine, and at the end we'll address tangent. All right, so the equation that we are going to do together is sine 2x plus pi over 2 plus sine of 2x minus 3 pi over 2 equals 1. So let's jot that down. Make sure you have our parentheses in the right places so that we see you have a sum and a difference inside your argument. So you're doing the sum or difference first. Now, we already know that we can't just make this sine of 2x plus sine of pi over 2. And we can't just split it up, sine of 2x minus sine of 3 pi over 2. That doesn't work. And if we did try to do it like that and we got an x equals, then when we go to check it on our graph on Desmos, it wouldn't check. We will kind of incorporate doing it by hand with our graphical reasoning. So when I look at this, I go, oh, this is not an easy looking equation to solve. And I don't like seeing those sums and differences in my trig equations because I know it's going to require me to use these formulas. And keep in mind, this is actually two pieces, one sum, one difference. So we're going to have to use the sum formula and the difference formula, and this is going to be kind of a long expansion. So in practical terms, if it were me solving this equation, I would probably go for a graphical solution first, to be honest with you. I would take a look at what in the world is going on with these two and how does that work. Now, it is important to be able to solve by hand and use the formula. So we're going to do that first, and then I'll walk you through kind of my Desmos approach. So let's remember our two formulas. So let's take a look at our sine. If we take a look at sine of u plus v, that's going to be sine of u cosine v plus cosine u sine of u. So make sure you've got that one copied down quickly. And then keep in mind this guy is going to look the same. Plus or minus here correspond. The plus goes with the plus, the minus goes with the minus on sine, and then we saw that flip on cosine. Okay, so we need to just remind ourselves. Oops. And let's go ahead and plug in. So again, this one is going to have two terms and then two terms. So in this case, maybe we should have done this in different colors here. Let's put some blue on this. So let's go ahead and take our first box. So for the red, let's go ahead and split this up as, here's my U, here's my V. So I'm going to write this as sine of 2x cosine pi over 2. And then keep in mind, I'm still using the plus formula, plus cosine 2x sine of pi over 2. Now, just to make things easier, and so I don't have a giant whiteboard where I can keep on going, I'm going to stick the plus, this plus, right here. Okay, and then I'm going to continue in blue for this second part using our minus sign down here. So in this particular part, our u is still 2x, and our v is 3 pi over 2, and we're using our minus formula. So keep in mind, I've got the sum of those two things, and then I'm going to write equals 1 after this. So at this point, I've got sine of 2x cosine 3 pi over 2 minus cosine 2x, and then sine 3 pi over 2. And then all of that, I don't have a scroll feature on this iPad part either, that would be nice, is going to be equal to 1. So this doesn't look really better yet, but keep in mind, cosine of pi over 2, sine pi over 2, those are special, right? I can go ahead and replace those. So if I think about the cosine of pi over 2, my 90-degree angle, and my cosine is going to be 0. So if this is 0, think about this entire term. Since we're multiplying by 0, zero's out. It's gone. And since sine of pi over 2 is 1, all of that is just going to be cosine of 2x. So I'm going to squeeze this in below here. But all of the part in red, maybe I should make it red still, became cosine of 2x. And then take a look at the blue part. If we think about cosine of 3 pi over 2, that's our bottom of our unit circle. So the cosine is going to be 0. And then our sine is going to be -1, since we are at the bottom and in the negative part. Then if we think about minus a negative, that's just going to turn to plus. So let's go ahead and fill in this part. So notice this guy is all getting zeroed out. That's going to be plus whatever this guy is. Okay, so filling in all of the blue stuff simplifies to this. And then I still have that equals 1. We don't want to forget it's an equation. If we leave off the equals 1, it looks like we just have an expression or maybe part of an identity that we're trying to prove. Cool. So that was a lot of work to get here. Before we finish, questions on this part? What you're going to see in practice is that when one of the u or v is an actual degree, particularly one of your special ones like pi over 2 or pi, something like that, then you're going to have big parts cancel out. Or if this were something like pi over 6, we wouldn't have cancellations, but we would have some numbers in here. Could potentially get nasty in terms of finding those. So let's talk about what to do here. Notice we have cosine of 2x, cosine of 2x. We can actually think about this as now 2 cosine of 2x. There's 2 of those cosine 2x pieces. You don't want to say that this is cosine of 4x. You can't multiply on the inside, just like you can't split up and take them apart with addition. It doesn't work. But we have this. So this is kind of nice because if we're thinking about what we did last week and we isolate the trig function, we want to deal with that inner part and undoing it first. So the cosine of 2x is 1/2. Now I want you to just think about this. If that's your u, you could now think about, okay, what is that angle? What is the angle that I'm looking for, ignoring the 2x? In other words, if that's question mark, what's question mark? My brain has to think about it like that. Otherwise, I get a little bit ahead of myself. So in this case, I have to think about a few things. I have more than one quadrant. And I want to think about all the places where my cosine is 1/2. So if I think about my cosine could be 1/2 in my first quadrant, in other words, where it's going to intersect here, and then 1/2 here. So that should be my 60-degree or my pi over 3. But keep in mind, we haven't taken care of that other 2 on the 2x part. Or this could be negative pi over 3, but let's write that negative pi over 3 as 5 pi over 6, so that we're thinking about between 0 and 2 pi. Okay, so I'm gonna write like this. My angle before I divide by 2 is that part. So what that really is telling me is I have two pieces. 2x equals pi over 3, and I have 2x equals 5 pi over 6. So x equals pi over 6, and x equals 5 pi. Oh, hold on, guys. I wrote 3, and then I wrote a 6 here. What did I do? Make sure I said it, and I'm not sure if I said it and wrote the right thing. Let's go back to it. So pi over 3 and negative pi over 3. So let's see. Oh, this should be 5 pi over 3, guys. I'm sorry. I wrote the 6. See, good thing to go back and look at it, because I was wondering, where did that 6 come from? So let me correct that, and then we'll correct that here. So here, 5 pi over 3 is really the same thing as the negative pi over 3. So we're thinking 6 pi over 3, or 2 pi minus pi over 3 gives me that 5 pi over 3. And I mistakenly just wrote that 6 and then carried it down. So if we fix that and divide by 2, pi over 6, 5 pi over 6. Now, keep in mind, this is a trig equation. So we said that if you find the angles between 0 and 2 pi, you could have multiples of those. And the multiples come in 2 pi's. But when you're looking at, in this case, dividing by 2 afterwards, you have to then divide the multiples instead of coming in 2 pi multiples or adding 2 pi each time. You just do plus pi in. You divide that 2 pi by 2, and you're adding multiples of pi. So this should be my equation, or my general solution. And it looks like if I just look here, I have my 2 solutions, and I'm going to be able to tell if I have the rest of them. Because if you think about adding pi, that's going to be 7 pi over 6. So we're going to pick up some extra ones between 0 and 2 pi as well. These ones are actually the ones between 0 and pi because of that period change. So before we go to Desmos and see if all of this is correct from a graphical standpoint, questions here? Okay, so I'm going to stop this share. Oh, we have someone joining us. Oh, there we go. And let's go ahead and I'm going to stop this share, and I'm going to share my Desmos. Okay, so it's going to take me back to the Desmos activity, but then I'm going to switch us over and get it to replace to just a blank Desmos screen. And we don't need this stuff anymore. Let me get rid of it here. Because what I want us to do is go ahead and adjust the viewing window for what we want to see. Keep in mind, we're still in radians, so I'm going to leave that. But I'm going to make my x-axis for right now go between 0 and 2 pi. Even though normally this period change means 0 to pi. And let's go ahead and make this steps of pi over 6. In other words, if you've done the by hand part, you can go ahead and see what that should do to make sure your solutions are easy to check. And keep in mind, I really don't need to mess with these y's, so I'm not going to, especially if you're multiplying by 2 or adding things together. You could have a value that's higher or lower than 1 for your particular trig functions. So what am I going to put into Desmos? What I'm going to put in to start, kind of like we did last time, is the very original equation with the entire equation and the equals. So it takes a second to put in because it was gigantic. But 2x plus pi over 2. Okay. Then we had plus sine of 2x minus 3 pi over 2 stuff. And then all of this was supposed to equal 1. Now, notice what just happened. Before I put that equals, we had a nice sine curve because we're adding 2 sine curves together. And according to what we did on our by hand work, when I add those two cosine curves together, send them through the addition formula, they actually simplify to two cosine curves whose argument matches up, so they're aligned. We have the periods line up. But either way, when we hit the equals 1, now all you're seeing is the solutions. Take a look at your solutions, and I see the pi over 6 solution. I see the 5 pi over 6. Then if we add pi over 6 plus pi, that takes me to 7 pi over 6. 5 pi over 6 plus pi takes me to the 11 pi over 6. And then I'm going to have those multiples just continue. In other words, this is what we did. This is our first repeat. So let's go ahead and break this apart by looking at the left and right side, because that part is interesting. Let's put this back up. We want to connect to the geometry of what's going on too. Now, what happens if you're wrong? Then you may want to consider going back and kind of doing like an identity to check every single step. As long as you're putting equals 1, you're just manipulating one side. So if you can keep on manipulating one side and nothing changes, then you can find the step where your mistake is. So in this case, let's put this back in, 2x minus 3 pi over 2. Oops. You guys can see, like if this guy simplified, it's kind of cool when you are building this, because you can see that these two sine functions, their periods don't line up, and you have this noise and kind of a new periodic function that's a combination of the two. Okay, so there we go. And then if you think about on your next one, the line y equals 1, notice you're seeing those periodic intersections happen. So this is a useful technique, but it's a useful technique only in kind of book problems, maybe occasionally in some real life problems, but very rarely would we write a trig equation that's set up so that everything cancels out nicely and then we can solve it by hand. Most likely, if you're doing some sort of modeling problem, you're going to be doing graphical solutions because you're not going to be able to get exact answers like pi over 6, 5 pi over 6, things like that. So questions here. Let's talk briefly about the tangent. So far in the course, we've focused on sine and cosine because we know we can always get tangent by doing sine over cosine. And that's really what I want you to do when you're finding exact values for tangent, if you need them. Again, the WebAssign focuses on sine and cosine too. But for example, let me go back to this one because I want to focus on our 15 degrees and our sine and cosine, or I should say our cosine, our x, and our sine, putting those in the right order. So if you know your cosine and you know your sine, then you could find your tangent by doing a division. Now, is it going to necessarily be quick and easy? No, because we're going to have some radicals in the bottom, but we could clean it up. Most of the time, I think that is easier than going through and applying the sum and difference form for the tangent, and then having those individual tangents. But that's kind of personal preference. When I'm thinking about like what I know and what is ingrained in my brain, this tangent, sum and difference are not there. They're not ones that I memorized because I know that I can go through my sine and cosine if I need to. And while these might be helpful, I know I can look them up. So let's go through, and I'm going to stop this share and illustrate what I mean for the 15 degrees. So let me share iPad screen one more time. And what I'm going to do is just go to our sum and difference, and we're going to remind ourselves cosine of 15 degrees. I'm going to pull that work we already did. So we had cosine and then sine. Okay, so let's clean up this tangent a little bit. So if we did sine divided by cosine, we'll have our sine. And then instead of dividing by our cosine and making this look like a complex fraction, dividing is the same thing as multiplying by the reciprocal. So we're going to multiply by our reciprocal of our cosine, which is the same thing as dividing by cosine. So notice our 4's cancel out. And if you wrote this, I'd be happy. Now, is this the answer most textbooks are going to give? If you had it, no, because they might ask you to rationalize the denominator, which, y'all, does not seem to be worth our time. In other words, get those square roots out of the bottom, which if I wanted just a decimal approximation, I could type this into Desmos and get it. And again, I'm happy with this. Okay, so if you were to use the trig function formulas, you might not get something with radicals in the denominator. It may clean up a little bit differently, but it should simplify to the same decimal. If you want to take it further, go for it, but definitely not required. If you have somewhere where WebAssign counts your answer wrong and you think it's because of radicals in the denominator, just let me know. I can override those. So questions here. Okay, so let's talk about what you need to do. In terms of Desmos activities, the Desmos activity that I showed you, that's the only one that you're going to have for this particular section. And your WebAssign is edited down. I think it's about 10 or 11 questions now. It focuses on the first few problems are just writing down the formulas, like just copying them from the textbook or from that, just right into the WebAssign part. Then you're going to have some practice kind of splitting up. You have a little bit of trig identities with the cofunction. Maybe we'll look at that one in a second. And then you have a different trig equation. So let's go ahead. What I'm going to do is go into our WebAssign, just kind of show you. So let me get that open and then I'll share my screen here. So we'll go ahead and share it. And these guys are a little out of order, but you have your 5.1 through 5.4 at the bottom here. And you can go ahead and view that 5.4. And actually what I'm going to do, it pops up a new window on my screen. Let me switch it to student view real quick. Okay. So once we get into 5.4, you can see those first few are just the formulas. And then you guys are going to find exact values and kind of compare and contrast the idea of what it does when you add the arguments or add inside and then splitting them up. We should see that these are usually not the same. For the same reason, the one we did pi over 4 and pi over 4, I believe, with a cosine. And you're going to do the same thing here. You're going to work on exact values. Both A's in these ones are going to involve the formulas because you're going to have to use your cosine sum and your sine difference. Whereas in B, you're going to be finding your exact value and then adding those exact values together. So the idea is to put this together, like what you're doing in number 7, into like number 9. Keep in mind your randomizations may be a little different, but this one is going to work with a 7 pi over 12. So they tell you how to split that 7 pi over 12 up, and then you are going to use your sum formula to find your sine, cosine, or tangent. Or if you're thinking about the unit circle and you already did that Desmos activity, you already have your pi over 12s filled out. So you can go to your 7 pi over 12, fill in your cosine, your sine, and then do your tangent. Again, I'll have to check the coding on this, like what it will accept, but don't worry about simplifying your radicals on tangent. Okay, so you have exact values for 15 degrees. And then these last two, number 12 is an equation kind of similar to the last one. And then number 11 is an identity. Sorry guys, I thought that thing was silenced. I unsilenced it. Where you've got to use the cofunction identities. So for this one, you're verifying the cofunction identity sine of pi over 2 minus x equals cosine of x. So we know that's true. They're phase shifts of one another with a period shift of pi over 2. And what we want to do, it looks strange, but we're going to apply the difference formula for the sine to break it up and fill in the missing pieces. So it's like our u is pi over 2, our v is our x. So you have sine of u times cosine v. So in here you would have your pi over 2. And then you would have your sine of v. So this would be sine of x. So you're trying to manipulate this and then simplify. Notice we have the idea of substituting cosine of pi over 2 and sine of pi over 2. Sine of pi over 2 is 1. And then we're still pulling down that sine over x. And then this simplifies to cosine x. Okay. So again, you're not going to have tons of these. Every one should be very, very similar to this number 11. All right, so I'm going to stop this share. Questions here? I know this one was a little bit more abstract in our introduction, like why do we need this new formula? Keep in mind, we still did not address why this formula works. In other words, we said why it's true that you can't just do cosine A plus B equals cosine A plus cosine B. You can't just break it up like that. But we didn't really address why the formula is what we saw, right? We just said, oh, it's not that, but here it is, right? To actually figure out why that formula is what it is a little bit beyond the scope of what we have time for. So again, understanding how to find our pi over 12s or our 15-degree increments, and then how to use our identities and use these formulas in identities or equations is our main goal. So what you guys need to work on from here is your Desmos activity. I'll get that link up in just a few minutes so that it's there for you guys. And then your kind of shorter WebAssign for 5.4. When we take a look at 5.5 on Wednesday together, again, that will be our last section. And it's kind of similar. We're going to look at double angle. And although it's not required, I'm going to show you a little bit of half angle formulas and talk about the usefulness of those and where you would see them show up a little bit more. So I'm going to go ahead and one last call for questions, and then I'll end our session and get this stuff uploaded and our links active. All right, so I'm not seeing any questions. Thank you guys for being here and participating. Let me know what questions you have. If we have questions on this stuff or kind of going backwards, either send those to me via email and I can take a look at incorporating those into Wednesdays and kind of doing those live, or you can always drop it in the chat box at the beginning of Wednesday. We have a little bit of time because our 5.5 is not necessarily going to take as long either. We'll have a little bit of breathing room here at the end. All right, guys, so enjoy the rest of your day. I'll go ahead and end the session and see you guys Wednesday.